to be here today just to share with you some work that we are doing, and also all of the role, also the work that reservoir evaluations contribute in the CCUS value chains. So usually when people talk about reservoir evaluations, most likely everyone gonna think about like how we gonna know where we have oil or gas, or to extract oil and gas. But actually we do have another role that our main scope for reservoir evaluations is to find or to analyze or to get the reservoir characteristic, which gonna give you more information about the subsurface structures. And that's why it's gonna be kind of like important. It's also played like an important role for in this CCUS value chains. And yeah, we can go a little bit deeper in the next couple of slides. But the very first thing I would like to discuss with you, most likely all of us already heard about CCUS. However, we don't know exactly like how it's work and what is the change, the value chains of this CCUS. So CCUS is standing for carbon capture, utilization, and storage. And this process aim to reduce the CO₂ emissions to mitigate the climate change. So at first, at the very first of the process, we have the carbon captures. This involves capturing all the CO₂ emissions from the industrial process, like power plants or directly from the airs. And the technologies are used to separate the CO₂ from all the gases from the industrial, and preventing it from entering back to the atmosphere. And then after we capture the CO₂, then we're gonna start thinking about like how we're gonna utilize our storage. But before utilize our storage, then we need to think about like the way to transport it, right? So to transport the CO₂, there's two common ways at the moment that we are doing. Is the first thing is we move the compressed CO₂ by shipping it, or we also can transport it as through the pipeline. Then from there, we can transport the CO₂ after they separate from gases. We can transport to utilize it, or we also can transport to storage. So I would like to first to talk about like the utilization part. So basically, all of the captured CO₂ at this moment can be repurposed rather than simply just being stored somewhere, right? So for utilization involves this using the CO₂ in various applications. We also can use it either in enhanced oil recoveries, which we're gonna discuss in the next slide. For this process, basically, in the basic information that I would say is that we're gonna collect this CO₂, and we're gonna inject it back to the oil reservoir and help to extract more oil. So as you already know, after we drill the wells, the oil with the pressure from the wells, it's gonna start producing oil by itself. But after sometimes, like usually it's after around 20-30 years, approximately, then the pressure start reducing from the reservoir. Then we have to find a way how to bring the remaining oil up to surface. Then in this case, we start thinking about injecting CO₂ back into the wells to enhance the oil recovery for at this stage. Yeah, and then if we don't utilize it, then there's another way for the CO₂ to be in this value chains, that we're gonna storage this CO₂ either onshore or offshore subsurface, right? So for this method, this is gonna be the long-term storage CO₂ underground under geological formations. And these formations could include the depleted oils or gas field, or deep saline aquifers, or even unminable coal seams. So the idea for this storage is to securely store the CO₂ for 1,000 years, ensure that it doesn't escape back into the atmosphere. So in these chains, our reservoir evaluations role is it can be applied in this storage part, or it also can be applied in the utilizations, where we use it to find or analyze the characteristic of the reservoir for oil enhanced recovery, or to look for the reservoir to store the CO2 under the ground. Yeah. So then now we need to understand why CO2 storage and utilizations. So the CO2 storage and utilizations is play a very important role in addressing the climate change and supporting transition to the low carbon economy. So the very first thing I would like to share is mitigating the climate change. For the CO2 is one of the primary greenhouse gases, as we already knew. It contributes to the global warming, and by capturing or either storing or utilizing CO2, we can reduce the amount released into the atmosphere, and it's going to help to keep the global temperature in check. On the other hand, it's also supporting the net zero goal. Many countries or companies have set the net zero emission target. CCUS is one of the few technologies that can help the industries with the unavoidable emissions, like steel or cement, to reach this goal. Right? Because if they cannot reduce the emissions, then they have to find, or we have to find a way how to storage or utilize it. And the third one is enhance the energy securities. So for the CO2 utilization, particularly in enhanced oil recovery that I mentioned in the previous slide, it can help to maximize the extraction of oil from the existing reservoir, as to reduce the need of drilling the new wells or looking for the new wells, and providing a secure energy supply while transitioning into the renewables energies. And last but not least is the industrial applications. So all of the capture CO2 can be used as the raw material in various industries, including productions of synthetic fuels, building materials, chemicals, or even in food and beverage that we are having daily. And this promotes circular economy by repurposing the emissions. That's why CO2 storage and utilization is very important, and this is the things that we are looking for, and we have to improve it to addressing the climate change and supporting the transition to the low carbon economies. So now, what is the role of reservoir evaluations in this CO2 storage? So as I mentioned, the reservoir evaluation, it can be applicable for either utilizations or storage. So in this case, the reservoir evaluations, it plays a very important role for the storage. Is identify the suitable geological formations to be safe and effectively store the captured carbon dioxide subsurface. And also based on the reservoir evaluation, we also ensure that we have the long-term containment through the detailed analysis of the factors, characteristic of the reservoir, like porosity, permeability, rock properties, and also the integrity of the cap rock itself, which is very crucial for preventing CO2 leakage or maximizing storage efficiency. So the reservoir that we are looking for CO2 storage is either depleted fields for oil, gas, or for oil or gas fields, or we also can look for the salt formations or the aquifer, the salty aquifer reservoir. Those are the reservoir or the target that we are looking for. And usually, if we don't actually run on the surface of reservoir evaluation, we don't know about the characteristic of the subsurface, we will not be able to know where is a suitable place to store the CO2 down in the subsurface. Right? So there are some key parameters in the reservoir evaluation for the CO2 storage. I would like to group it in three big group. The very first thing is the reservoir properties. So if you look at the left side, this is one of the example for one of reservoir evaluations log, the graphical log that we present to our customer. Beside that, we also do convert this graphical to the digital data in case in case if we need to run like any modelings or reservoir modelings. However, this graphical log is give you like the general idea and information regarding the porosity, permeability, resistivity of the formation itself, the thickness of the reservoir rock, temperature and pressure and subsurface, and even it can give you the borehole image, the phases identifications, or the thin bed reservoir. So for example, if you look at that, I just give like very basic informations based on this log. For example, if you look at on this scale on the screen, with the gamma ray, it can give you the general idea regarding like if that is a saline zone or is this a clean sands. And based on the characteristic of the formation and the clean sands, we also can look at the porosity, the density porosity and neutron porosity to analyze and see how good is the permeability or the porosities of these formations. And also compare, we also do correlate with the resistivity in the formation as well. In this log, for example, if you can see from the resistivity curves, there's some separations in this curve, which is a good evidence to show that there's invasions in the formation, which means that there's a porosity, permeability, good permeability in this area. And it also reflects with the resonant magnetics data. So basically, for each of the data, the reservoir evaluation data that we collect, we're going to put it together and we're going to correlate it by depth. And from there, we're going to give the best answer to our customer or to the partner regarding where is the cap rocks or where is the source or where is the reservoir zone, and also have higher technology to analyze about the integrities and also the geomechanical properties. So long story short, for the porosity, usually if we look for CO2 storage reservoir, then the porosity is indicate that the storage capacity. And it's very important information that we need to know because it's going to tell you how much CO2 in the how much CO2 that the reservoirs can hold. And the second thing is the permeability. It's affect the injectivity of the CO2. So when we look for the CO2 storage, usually we're going to see how good is the permeability, how it's going to affect in the injectivity process, and also how easy the CO2 can flow through the reservoir. Yeah, and beside that, it's also provide you the temperature and the pressure. This information is very critical because it's ensure that the CO2 can remain in the supercritical states, maximizing the storage efficiency. And also, the thickness of the reservoir rock is contribute to the total storage capacity. So it's going to tell you the capacity of the storage area, how much you can store the CO2 in the reservoir. And of course, all of this information is going to be correlated with depth. The reservoir depth is also very crucial, not in reservoir, not in CO2 storage, but also in the reservoir characteristic in general. Because if we want to talk about like, we have the good zone or good formation, we need to know which depth is that the reservoir or which depth is the cap rock. And the reservoir depth is also crucial since CO2 need to be stored in the supercritical state. So we typically require the depth have to be greater than around 800 meters in TVD depths. In the cap rock integrity, the reservoir evaluation is also give you the full picture about the integrity of the cap rocks. For CO2 storage, we aim to look for the good cap rock and also good integrity of the cap rock by looking into the porosity and permeability of the cap rock, the low porosity and permeabilities in the cap rock layers. It's very important to prevent the CO2 leakage in the future or for the long-term storage. And also the capillary entry pressure determines the cap rock ability to resist the CO2 intrusions. And with high entry pressure is needed to act as a seal in this case. So with reservoir evaluation, with the service that we are providing, we also can provide the information regarding this cap rock integrity. And of course, last but not least, for the cap rock integrity, when we talk about the cap rock, is about the thickness. Again, with the storage for long-term storage and with high pressure of the CO2 inject into the formation, into the reservoir, then the thicker cap rock layers is going to provide a better containment. Additionally, we also can get the details of the geomechanical properties. The very first thing that the people can think about is about stress regions. We know that we can pump the CO2 into the reservoir, but then we also need to know, we need to have knowledge of the in situ stress of the rocks or of the reservoir itself. It helps to prevent the fracturing during the CO2 injections. So this gonna be is gonna give you the limit of the rock, how much pressure you need to inject to avoid creating fractures while injecting CO2 in the formations. And also the fracture gradients and the rock strengths. All of these informations help to assess the likelihood of creating or reactivating the fractures that it has in the formations or in the reservoir, which potentially lead to CO2 leakage in the future during the storage period. Last but not least, faults and fracture is something that all of the customer or all of the partner they are looking for, because whenever you look for the reservoir to store CO2, then we have to avoid all of the faults and the fracture to prevent leakage again for storing CO2s. And the presence or orientations or the stabilities of the faults and fractures, it need to be evaluated carefully during this reservoir evaluation stage for the potential CO2 escape path in the future. So basically, for the reservoir evaluation, we could, based on our technologies in general, we could be able to provide all of the reservoir properties. We also can tell the cap rock integrity, the geomechanical properties, and also we can see or we can tell about the connectivity of each reservoir to see if there's any connection, vertical interference in between the reservoir, or also connection from one reservoir to another. And I would like to move to some technologies that we use in our reservoir evaluations. The very basic package that we usually use, and it's basic for all of the reservoir evaluation services related to the well loggings, which we can provide the resistivity tools. We apply all of the physics and also the chemical knowledge to analyze and also provide the information of the subsurface. Based on well logging with the resistivity tools, we use the radiations reactions just to also to analyze and to collect to get the data of the density porosity, neutron porosity. We apply the physics of sonic to analyze and to get the data for the sonic, the total porosities. And beside that, we also have some technologies to detect or to evaluate lithologies of the formations, and also resonance magnetic tools to give you the cutoff, the porosity and permeability of the formations. On the other hand, with the reservoir evaluation, we also do provide the seismic survey. In the picture here, you could see that this one is the surface seismic survey, where we can operate with the board and it's going to see based on the transit time of each layer when it reach to each layer and it reflect back to the hydrofold. We can easily identify either fold fractures or different formation, different layers in subsurface. If we have to run with the well loggings by connecting tools with our E-line cable connect to the logging unit, then we also can provide the zero offset or the offset seismic with the wellbore with the tools down in the hole, and we're gonna find the source on the surface, and it's gonna start recording the seismic survey with the tools in the hole in the wells. Not only that, usually the clients, when we or our customer or partner, usually when we come into the reservoir fluid or reservoir informations, it's also very crucial or important for them to know what kind of fluid they have in the formations. And the only way for them to do that is to take the sample subsurface. We can run the equipment down to the depth where they want in the reservoir. After we already run the basic services with density and neutron porosity, we can analyze and also give the information regarding where is the reservoir. Then we're gonna continue to run the next service with the formation testing tools or the sampling tools, where we can get the formation pressure from the reservoir. We can get the temperature from the reservoir itself as well. And especially, we also can get the fluid sampling, the fluid sample. With the tool, the service itself, it can tell or it can analyze what kind of fluid we have down there, what is the contaminations in the fluid, if the fluid is water or it's going to be filtrate or it's going to be hydrocarbon or the compositions of the hydrocarbon. We can analyze it through the optical sensor in the tool string, and we can provide the data in real time. After that, depend on the demand of the client, we can take the sample up to the surface. Then we usually call it the PVT sample. We bring it up to the surface. Either we can keep it with multiple phase or single phase, or we can keep it with multiple phase when it comes to surface. And the client will use those samples sent to the lab, and they can analyze the fluid from the lab, and they get even more detail of the fluid informations from the reservoir. And there is also another service that we also provide with our reservoir evaluation services. Is providing the core, the infill core. Usually we call it the sidewall coring. The reason we call it sidewall coring is because it's the same. For example, if you look at this tool, we call it sidewall coring because when we low down, we can go to the precise depth. For example, if the client want to take the core at the depth 3,101 meter, then we can load down the tool to the same depth, and the bit is going to extract from the tool and cut the core and bring back to the core barrel, and then we can bring the core back to the surface. And the clients, usually the client gonna go also with the conventional coring while drilling. However, it's gonna be the long piece with long intervals. And then they do need the core, the infill core from the wildlife with the precise depth also to compare and also to get more detail of the core information. Also infill to the depth or the interval where they are missing with the conventional coring. And again, with this sidewall coring, we can stop and take the core at the precise depth where the client wants. So usually we gonna with one run of this sidewall coring, we can take up to 50 cores and bring it up to the surface. And depend on the demand of the client, we're gonna have different size or different drill bit that we can get different size of the core, either 1.5 inches or 3 inches, or nowadays we also have 3.5 inches cores as well. Last but not least is part of the high technologies of reservoir evaluations that we can perform also the vertical interference test to see if there's any connection in between two layers or in between the reservoir. Or we also can perform the stress testing by create the microfrac in the formation to see the opening pressure. propagation pressure when we try to inject to the formations, and also the closing pressure when we stop the fluid pumping and then see the pressure to close the fracture. And we do have also the new technologies which we can discuss in different topics, that we can provide deep trenchant testing. If some of you work in oil and gas, you might know that we have to do the true stem test as well with the testing, where we have to flare and burn a lot of CO2. But with our new technology with deep trenchant testing, we can see or we can use this application to pump and see how what is the radius of investigation to see how far the fluid can move, and also can perform the test without flaring as well. But however, that one is different topic. But in this case, it can apply to see that what is the boundary of the reservoir, and also it can apply to see the connectivity in between the reservoir or between the layers. Yeah. So this is just the summarize for the technologies that we are using in reservoir evaluations at the moment. And with all of these technologies, with all of these informations, after the wildlife trip, which most of the client they usually call reservoir evaluation is wildlife services. So after this service, we're gonna provide a full package of the well's characteristic or the reservoir characteristics. Then the client can start analyzing and give the decisions, or even they can give the decision in real times. What can be the next scope or the next target? Yeah. So after we applying that reservoir technologies to provide information, then we have to also understand about the CO2 storage mechanisms. So if you look at the graphics in this slide, yeah, in the x-axis is going to show you the time since the injection stop after you inject the CO2 into the reservoir. And the y-axis is going to show you the percentage trapping contributions of the CO2 based on the different mechanisms. So the very first thing at the very early stage, usually at 90% or even more than 90% is going to go with structural or stratigraphic trappings, which you can see the purple in this plot, in this graphic. And as I mentioned initially, most of the CO2 is going to be trapped by this physical barrier like caprock, basically, and the reservoir. After we provide the information of the reservoir evaluations, then with this structural and stratigraphic trapping, usually this is gonna be the least secure method, because the leakage, it can occur anytime if the seals is compromised. That's why it's very important for us to analyze and provide the correct information regarding the reservoir and also the caprock's integrities. This is gonna be crucial for to make the decisions for this CO2 storage. When it moves, usually this structural and stratigraphic trapping is going to take the time at the beginning from the first year after injections up to 10 years approximately. It's going to take around 90% contributions of the CO2 will be trapped with these mechanisms. Then it's going to move to the next step or the next how you call it, like mechanisms, trapping mechanism is what we call it residual trapping CO2. Then at this time,
sorry to interrupt, but can you wrap up pretty soon now, because time's running and we would like to have room for a few questions afterwards. Thank you.
Sure. Yeah, so the next, for the medium one is going to be residual CO2 trapping. Yeah, so some CO2 is going to be trapped in the small pore due to capillary force. And then the next one is going to move a little bit when it takes longer time, over 100 years to 1,000 years, is going to change to the CO2 is going to dissolve in the formation water and reduce the risk of leakage. And then after that, longer, like over 1,000 years, then it's all of the dissolved CO2 is react with minerals to form the stable carbonate rock. And this is the most permanent and secure form of the CO2 storage. And this is also what we are aiming for, the long-term storage. Yeah. And I would like to introduce one of the case study in Norway for the Sleipner CCS project. This project in the Norwegian North Sea is started in 1996, and it stored the CO2 in the Utsira sand formations, a deep saline aquifer in the North Sea. So as you can see here, at the very first stage, as I mentioned in the previous one, from let's say 10 years, most of the CO2 is injected into the porous sands reservoir, if you can see in the graphic here. This reservoir is beneath the thick cells above. Yeah. And they are expecting after 20 years, this structural trapping is going to start reducing, and it's going to start increasing with the residual and solubility trapping mechanisms. It can increase up to 20 or 25% based on their predictions. And they aim to target for the long term with move up to over 50% of mineral trapping, and after that it's going to take over with completely mineral trapping in the future. Yeah, and that is what I would like to share with you during this seminar. And thanks for your time and attention. I appreciate if you have any question for discussion. Thank you.